Good day, everyone. My name is John Michael C. Evangelista, and now I am gonna present our assigned topic, which is a Bitonic Sort. First, let me present to you our introduction about Bitonic Sort. Bitonic Sort is a comparison-based sorting algorithm that was introduced by Ken Butcher in 1968. It is particularly notable for its sustainability for parallel processing environments, making it the ideal choice for applications that requires efficient data handling across multiple processors. The fundamental concept behind Bitonic sort involves transforming an unsorted sequence into a Bitonic sequence, a sequence that first increases monetarically and then decreases. These transformations allows the algorithm to leverage predictable patterns in data to perform sorting efficiently.
Time complexity of Bitonic sort. O log n squared. Time complexity of Bitonic sort. O log squared n. What is log squared n? Log squared n simply means log n times log n, or the logarithm of n multiplied by itself. If log n is, for example, 3, when n is equals to 8, since log squared 8 is equals to 3, then log squared n equals to 3 by 3, and it is equal to 9. The next is Bitonic sort involves two main steps: creating the Bitonic sequence, and the second one is sorting the Bitonic sequence.
Good day, I am Kyla Marie Galos, and I'm going to give a real-world scenario that applies Bitonic sort. So, in educational institutions, teachers and administrators often need to analyze student performance data to make decisions regarding academic progress. So, to implement Bitonic sort in data structures, student grades can be represented as an array of tuples where each tuple contains student ID and their corresponding grade. So, the goal is to sort these tuples based on grades in ascending order so that the teachers can easily identify the top performing students or those who may need additional support. So here is my example of the student ID and their corresponding grades. Okay, so to avoid confusion and mistake, I underline the grades of the students. So now, the tuples in this array is, so there is 8 tuples in an array. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to divide it by 2. 1, 2, 3, 4. So since 8 divided by 2 is 4, now we're going to compare it by the 4 arrow lines. This 1, 2, 3, and 4. So let's compare 78 and 97. So since 78 is less than 97, we're going to write it as is. 97. And then 85, compare it to 95. Since 85 is smaller than 95, we're going to write it as is again. 5 and 95 and so on. Compare 88 to 90. So, and compare 92 to 83. So since 92 is greater than 83, we're going to switch them. Now 83 is here and 92 is now. Then we're going to divide it again by 2. So 4 divided by 2 is 2. So we're going to compare it by 2. 1, 2. Okay. So 78 is less than 88. So we're going to write it the same. 85 is greater than 83, so we're switching them. And 97 compared to 90, so 97 is greater than 90, then we're going to switch them. And 95 is greater than 92. We're going to switch them again. So we're going to divide it again by 2. So 2 divided by 2 equals 1. So we're going to compare them by 1 our lines. So 78 is less than 83. The same. 88 is greater than 85, so we're switching them. 85 will be put here, then 88. 90 is less than 92, so it's just the same. And 97 is greater than 95, so we're switching them. 95 and 97. So now we have 78, 83, 85, 88, 90, 92, 95, and 97. Now we have the ascending order of the grades. The lowest grade, which is 78, belongs to student ID 103. And the highest grade, 97, belongs to student ID 108. So now, after sorting this array, it is now clear that student ID 108 is the top performing student, while student ID 103 needs to be supported in class.
Good day, I am James Kapuyan and I will be discussing the assessment of Bitonic Sort. The strength of this algorithm is a parallel sorting algorithm that excels in environment with multiple processors, offering predictable performance and simplicity in implementation. And the weaknesses of this algorithm, it is not in place, lacks stability, and is less efficient than other algorithms on sequential machines, making it best suited for applications in parallel computing and hardware implementation. And lastly, the application of this algorithm is primarily applied in parallel computing environments, where it is efficient to sort large datasets by leveraging multiple processors to perform comparisons simultaneously, making it suited for hardware implementations and applications requiring predictable performance in sorting operations.
So, for the conclusion, Bitonic Sort is an efficient parallel sorting algorithm that uses the concept of creating a Bitonic sequence, a sequence that first increases and then decreases, or vice versa, and then sorting it. It is particularly well suited for distributed systems and hardware implementation due to its parallel nature. Although Bitonic Sort has a time complexity of 0 log 2n and is less efficient for general-purpose sorting compared to algorithms like quicksort or merge sort, its deterministic structure and ease of parallelization make it valuable in scenarios with parallel processing is crucial, such as GPU programming and network systems. In summary, Bitonic Sort is not optimal for single-threaded use but excels in parallel environments, showcasing its relevance in specific computational contexts.